Let's start. So, what is game theory? So, those of you do not know, game theory basically is a branch of mathematics which studies sort of this interactions between rational agents. What does rational agent mean? Rational agents are people who have some type of incentive and they are acting in a self-centered way, and self-centered does not mean malicious. All they want to do is basically maximize their payoff, their situation, okay? And we will see what that precisely means as we go along. So, that is what we mean by rational agents, as opposed to irrational agents about whom we can't really argue. We don't really know what they want and so on. So, with rational agents, the very least we know about them is that they are just trying to maximize their payoff. Now, that comes at the cost of other people who are also participating, who are interacting with them. So, in the effort, in my attempt to maximize my benefit, I might actually do something, I might take a course of action which might impact the other person adversely. Okay. So, that is the competition. Cooperation might be something where, well, I realize I am in a situation, and we will see something example where the only way I can sort of get any payoff, let alone maximize my payoff, is by cooperating with other people. Okay. So, this is why it is really the way people, rational agents, would interact, be it cooperation or be conflict. Okay. So, let us see, start by, okay. So, we just talked about maximizing payoffs, right. So, if we say who are self-centered, so that basically just means trying to maximize their own payoff, okay, payoff or gain, whatever you want to call it. So, then if this is the case, if we are just trying to maximize payoff, what do you think is the difference? Why are we even talking about game theory? That seems like something that should just come well within optimization theory. So, you know what is optimization theory, right? Where you are trying to maximize or minimize some objective function. Is the question clear? Okay. So, okay, so can you give me an example where the two things are like you can see the difference between a normal optimization scenario versus a game theoretic scenario? I mean, you are right. The point about optimization is, when we talk about an optimization problem, we do not use terms like rational agents and people trying to maximize their pay. It is like there is a global kind of an objective, and whoever is trying to solve the problem, anybody is going to try to maximize. It is not like from a particular agent's perspective, like this person would optimize it this way, this person would do that way, right. So, a very simple example where I think this perspective, optimization versus interaction, comes through is if you think about, if I asked you, saying theory and I said true. Okay, I am going to need a wet wipe. Is like if I asked you to tell me a short between point A to B, find me the shortest path. How would you do it? You would look up a map, you know Dijkstra, you can find the shortest path from A to B, right. It is very straightforward. Everybody learns it in their first course in discrete maths or algorithms basically. Now, if I asked you what is the shortest route between A to B at a certain time of the day, does that meaningfully change the question?
I am not the only one traversing through it.
Yes. So, that is why when I say route, I am no longer talking about distance. See, distance is a new, like it is a global sort of value. It does not change with time of day, it does not change with respect to who is measuring and so on and so forth, none of that. But when I say route, I am sort of talking about, it was implicit in the way I was trying to say it, that there are other people on the road, and this time I am trying to minimize the time taken to travel from A to B. So, when there are other people on the road, our common experiences, we might actually encounter significant or at least noticeable delay, right. So, that is basically the point. So, the distance, shortest distance would correspond to the best route if there was like nobody else on the road, right. But because of the presence of the agent, other agents impacts how I sort of experience the amount of time taken to travel, even though the distance remains the same. So, oftentimes these two questions will have materially different answers, because one takes into consideration the load or the traffic on the road. Okay. All right. So, let us sort of try to see before. Okay, let us start with some simple example. So, you know this game, it is called TCP. I am sure it has other names. So, basically imagine a very sort of fabricated situation where there are only two people using the internet, you and some friend or colleague of yours. So, that is it. So, and they are basically controlling all the traffic over this internet. Now, so the TCP protocol basically is the rule by which traffic moves through the internet, right. So, the protocol has in itself a mechanism called back off. So, if the network is completely congested, the back off basically means that each of the users, in this case more generally, each of the users will basically hold off on some of the traffic, like they will pull back so that the traffic sort of becomes decongested and then they can again resume. Okay. So, that is the back off mechanism. So, I am not going to write it. So, you understand what the back off rule governing this is the, you can route as much traffic as you want until there is a back off when network is congested. Okay. So, this is how it would be played if it were played correctly. So, people have a choice to back off. If they do not want to back off, they do not back off. Okay. So, let us consider what happens between two people who are, so let us say you are the okay. Let us write correct. Okay. So, correct way means can you read this? I am writing correct and defective. Okay. Let me, my handwriting is already getting very bad, it will only get worse. It is hard to write straight actually. Okay. So, the way we represent this, this is sort of a standard way of representing games. Okay. So, when you have two player games, it is usually like this. You have this idea that one player, so each of the rows represent the actions available to one player, in this case you, and the columns represent the actions available to the other player. Okay. Now, of course, if you have multiple players, there is a natural generalization of a two-dimensional matrix, but then drawing it and writing it becomes absurd. So, then we just take on the sort of formal way of writing in terms of functions. So, for this at least we can manage to write here. So, there are only two actions available. It is like the when there is congestion happening, back off. If congestion is happening, you may just still continue to route traffic. So, that is like the defective way of doing it. Okay. So, this the row represents the rows represent your actions and the columns represent the action of the your colleague. Okay. So, let me write some values. Okay. using negatives, yeah. Okay. So, this how to interpret this is following. So, if both people are playing correctly, right, using the backoff protocol whenever needed, both of their payoffs will be -1 -1. Okay. So, this is a payoff matrix. So, in this case when you see negative numbers interpreted in the whichever way the normal way, payoff is something that we use when we want to try to maximize. So, they obviously want to experience least amount of delay, that is the objective here. So, if both of them are playing correctly, their sort of delay would, their payoff delay when sort of interpreted in terms of numerical values, it is -1 -1. When one person is playing correctly, I am playing, you are playing correctly and your colleague is not playing correctly, then you experience lot of delay, -4, okay. But your colleague somehow has an advantage. This is how it is to be interpreted. Similarly, this, it is a symmetrically opposite thing. You are playing, taking the defective strategy, your colleague is playing it the right way. So, that person sort of encounters delay, and if both of you are playing in a defective way, both of you basically suffer, both of you sort of encounter delay, and which is sort of worse than how much you would if you had both taken the correct route. Okay. Is the interpretation clear here? Okay guys, those of you who are online, please feel free to stop and just ask, unmute yourself and ask a questions. Okay. All right, because I am not really looking at the chat, I do not even know how. So, okay, somebody did I think they are recording, Pavan. Okay. Shiva, we are recording, right? Yeah, somebody reminded me. Okay. Okay. So, is the interpretation clear? So, now the thing is, there is really nothing very significant about these particularly chosen numbers. All I wanted to show was you have this sort of an alignment of interest, that if both of you play the right way, there is advantage to it. If just one of you plays the right way, the person who is not playing the right way gains an advantage over you. And if both of you play the wrong way, then then also the both of you sort of suffer the consequences, like that, it's sort of a thing. Okay. All right. So, in this case, can you tell me what should you do if you were faced with this situation?
As a person, just me individual.
Yes, this you as in one of the agents playing the game.
There is no cooperation.
You cooperate. What do you mean cooperate? Like do the correct thing?
Both agents can talk. I mean, both the agents can talk to each other.
No, at this point, no.
Then to -3.
But you don't have any control over what the other person is doing.
Yeah.
So what should you do? Should you play the correct way or defective way?
Defective.
I should play the defective way. Why is that?
Because well, if you play correctly, then why is that? In that case, you end up -4.
Okay, so let's start. So suppose we start with, if both were to be playing correctly, it would be a -1 -1 situation. This is really ideal. However, if this person, if I sort of, so I continue to play the right way, right? I continue to, so this means that I continue to play the correct way, but the other guy defects, right? The other person defects. So that person encounters a significant improvement in the situation, right? So that's what this is. Okay, so that person basically has a reason to defect, to play the defective way. So what he was saying is more so this, that if I defect, if I do the other thing, that I take the defective strategy, then basically I encounter an improvement in my situation. So that's one thing. So from here, it definitely seems like the row player should want to move to the defective this thing. From here, the column player should want to move to this thing, right? What about, and if you were from any other place, suppose I started from here, what should they want to do? What should anybody want to do? So what we are trying to say is there any situation, why is, so he said why defective is the thing that a rational agent would do. We are sort of I have no control over what the other person is doing, right? So my are both joint situation could be any one of these positions in the matrix. So, that is what we are trying to argue, like what is the rational agent's sort of driving motivation here. Yes, you were saying?
Yeah, so if we are at the third 0 minus 4, then the column player would try to like defect.
Yes, because he sees that right now from this he could definitely have an improvement by going here.
This part, like in that case, then the row player would want to defect.
Yes, because that gives an improvement, right? Correct. So, either way we see that each individual person gets at least a better payoff, at least better, right, if they just move to this column with this D strategy, defective strategy, right. And this is especially true when we have no control over what the other person is doing. This is what self-centeredness means, because if they both really cooperated, they really could have taken advantage of this situation, but that is not happening. So, each one individually arguing for themselves would see that, well, I do not lose out really, because I do not know what the other person could do by just choosing defective strategy. Okay? So, defective here means not backing off and being really, really selfish and so on. Okay. So, this sort of strategy, like this sort of thinking when it exists, is called dominant strategy. Okay? So, I will introduce these terms later on, but when
So, Smita?
yes.
Yeah, so I have a question. So,
Yeah.
if I replicate the opponent's strategy in the next step, so is it not better than always choosing the defective answer?
Okay. So, you are saying it's if it's a multi-round game.
Yeah.
Okay. What is it that you want? Okay. So, first round you did not know. So, you will say like I am going to do the defective strategy because I have no information. But in second round, what is it that you want to do? You want to take the correct
No, so I want to replicate the answer for the first round of my opponent. So if the opponent chose the correct way, then in the next round I will choose the correct way. If the opponent chooses the defective way, I will stay with the defective way.
Okay, but what is the guarantee that your opponent has not moved to the if they were doing the correct adopting the correct, like what is the guarantee that your opponent is not taking a different course of action in the second round? There is none. So, you move, your opponent has also moved, right. So, then you are at the back to the same situation. That is the idea. This was going to be one of my follow up questions, that if this sort of a thing progresses for multiple rounds, does our thinking really get us to a different conclusion? It seems no, primarily because I have no control or knowledge of what the other person is doing.
Also, like that's what I was thinking. Since both of them have this knowledge, right? That is going to be a multi-round thing, and both of us can observe each other. So in a way, like my opponent might be trying to elude him, like taking the wrong choices and kind of making me believe that I would also follow this.
But the point is, why is the opponent why would the opponent try to do that? The opponent's main goal is to minimize its own delay, like send as much packets as through, right? So this is why we started from this thing. Even if they start by somehow, by luck or something, they were actually doing the right thing. They realize that by doing the wrong thing, I will get a significant I do get a better advantage. This is what disincentivizes them to stay on that track, like to do the correct thing. Is it clear? Is that part? Shushavan, was the answer clear?
Yeah.
Okay. So, that's the main thing, right. So, we know, so this is, I will define all these things formally, but this sort of a thing when I can argue that this is the best strategy I can take irrespective of what the others are doing, that is what is called dominant strategy. Okay. Now, my question was, will all two users behave the same way? I mean, we have already sort of agreed on this, but let us sort of still ask, would any two users who play this game behave the same way?
In the same payoff matrix.
Yes. Sorry?
In rational players?
Yes, that's the point, and that's a very significant point. This basically dictates how any rational player would behave, right? It's not about individual players, but it tells you something very strong about a very large class of player, which is rational players. Now, if the player was not rational, if we would really not know what they would do, right? A rational players possibly, like, it's an absolute chaos. It's very hard to predict that kind of a thing. When you know that other person, no matter what, will always trying to they are trying to maximize their own payoff, right? If you knew everybody's payoff function, some argument can be made like this. Whether or not there is a dominant strategy, that's a different thing, but some amount of you can do some kind of argumenting for yourself to imagine what that person's possible actions might be. Okay, all right. What if they communicate with each other? Does that give them a reason to behave differently?
Is it still just one game or multiple?
Let's discuss one game and then we'll discuss multiple rounds.
Can they still like choose to lie about it?
What do you mean lie about
They
it?
say that.
Trust each other.
Yeah.
But what are they gaining by?
They say they'll choose correct and then defect.
Okay, so basically you and I are playing the game. I tell you I'm going to do this and then later on go do something else. No, let's say that does not happen. There are situations when that does happen, but that's sort of a much more a little, we'll get to that later. So yes, we can discuss before the game starts. We know this common payoff matrix. This is like what is called a complete information scenario. Now, can we now, after having discussed with each other, does that make us behave differently when the game actually starts?
Communicated truthfully.
Yes, yes.
Yeah,
You can go to correct.
Single round is multiple rounds.
the correct.
Let's say single round.
Yeah, we would stick to correct.
Why? I always know so this thing always is true, right? We start with correct, but if I change to the other thing, then I actually get it, because it's a one round thing. It's not like over time. So here, that was a good question. This is why. So if I am a untrustworthy opponent, in the subsequent rounds, whatever I say, you may disbelieve, right? So then I have no guarantee that you will actually stick to your correct one. First time, if you are the honest one, I am the dishonest one. So I know, okay, he is not going to switch. So I can choose to the defective strategy and actually gain, right? So this is why discussing ahead of time also gives us no reason to behave differently. Now, you all were asking, let's have a multi-round thing. How much can I really gain by sort of lying about it one time, right? Well, that really depends on how so first time I lie about it and I gain an advantage, do this, but from second round onwards, my opponent now knows that I am susceptible to lying about it, he also changes, right? So we are here, because that person has knows that I'm basically just being very self-centered regardless of what our plan was. I'm just basically taking the selfish route. So this person also ends up here. So in this particular case, when you have a dominant strategy sort of thing like this, multiple rounds don't seem to give us any benefit.
What if it were infinite rounds?
That's when the situation might change. Finite number of multiple rounds does not give us anything. What happens in infinite step games is sort of it's different. Then we don't know. And right now, from what I have told you, the math, I don't think you can sort of figure out why is it obvious why in finite rounds it's not, they are not going to behave differently, but the moment the game tends to infinite rounds, right? So the game is going on and it is sort of tending to infinity, that interpretation of infinity, okay? In a limit, then the behavior need not be that of a dominant strategy. So, we will see if we will get to that towards the end of the course, and that is a different point. Okay. So, that was a good point, that finite there is a difference between finite number of rounds versus infinite number of rounds. Okay. 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 So, if the values were to change here, okay, if the values were to change here, then could their behavior change? Like this sort of behavior, is it robust against how much change in values?
I mean, as long as the ordering is respected.
Good point. As long as the payoff structure is of this kind, really they have that dominant strategy will prevail. But if I sort of fudge the numbers a little bit and so on and so forth, then the situation will be, right. So, that sort of a value change means what exactly? If but then if too much value change basically results in an entirely different game, because the action, payoff, everything sort of changes. Okay. So, I do not give a conclusive answer to this, but that is the thing. Up to certain points, the values remains robust, and we will see at some point that usually when you have things like this, an affine transformation of the values. Okay. So, initially I was getting a value x, let us say. Now, everybody's valuation changes by this for a fixed a and b, then nothing changes. Materially the game remains the same, even though the payoff precise values might be different, but behavior, dominant strategy, all these other concepts that we will learn, they all remain the same. Okay. All right. Okay. So, on the people who are attending remotely, everything clear so far? Please let me know and please stop me. Okay.
Is this the positive way?
Yes. Okay. Yeah. Let us take one. Okay. There can be some, let us take this. Okay. Okay. For the moment, let us stick with this. Okay, a little bit more. So, obviously, here I being a rational agent, I am thinking about not only what is good for me, but what is good for me invariably is intrinsically dependent on what you are going to do, right. So, I am forced to think about what your behavior will be. That is the essential component here. My decision making about my thing cannot be independent of that. So, if I have a different notion of how rational you are and so on, would then the decision making change?
Different notion as well.
Good point. Suppose I did not know how much of this matrix you actually knew. Suppose the payoff matrix. So, in this right now what we were discussing is when we both have the exact same information. You being a rational player, I can completely sort of imagine what your possible thinking would be. But if you imagine a situation where I do not necessarily know how much of the matrix, how much of the payoff scenario you know, as you know in terms of what I know, what you know of what I know. Okay? That is what is generally called incomplete information setting. So, in that case, could their sort of logical thinking be conceivably different? Because we just discussed that all rational agents are going to behave this way, right. But in an incomplete information setting, can we still get to that same conclusion?
As rational players, we are using a defective strategy, then a person with incomplete information might try to play the correct way.
Yes, I really built into the term incomplete information is I do not also necessarily know which part of the matrix, which part is unknown to you, and unknown also means maybe you know not in a deterministic way, you are sort of estimating the values and so on and so forth. So, in that kind of a scenario, I can't necessarily argue this way that no matter what happens, taking the defective strategy gives me at least as good an outcome as taking the correct strategy. Okay. So, this incomplete information setting throws in like lots of other sort of mathematical issues as to what the logical steps would be and so on. Okay. So, this is something to keep in mind. As of now, I will always mention when we are talking about complete or incomplete for the foreseeable future, we will talk about sort of complete information setting, and if you are not sure, just ask. Okay.
Yeah.
Yes.
In this particular game, no matter what the opponent chooses, the defective strategy is best for us, right? So if the opponent has the complete information, it doesn't matter to us.
So, if you are saying that as long as I know the matrix, I do not really care what the opponent knows, how much the opponent knows.
Yeah, because we have the dominant strategy and there is nothing like.
Yes, that is correct. If I had complete information about this, but the opponent does not necessarily, right? Then also basically the definition of dominant strategy means that no matter what the other person does, this is at least as good a thing as I can do. Good point. Okay. So, that dominant strategy accounts for suboptimal behavior also on the part of the opponent. That behavior might be because they do not have complete information or they did not calculate things properly, whatever. Okay. But what happens in an incomplete information game is when you do not have a dominant strategy, then things can be like very alright and so on. So, we will see those things later. Okay. So, in general, let us try to now formalize what a game is. So, we know that games are different objects as mathematical objects than an optimization question. So, we will discuss what. Okay, I do not need this as of now, we will see later. So, can you tell me though, from what we have seen, what are the basic ingredients that constitute a game? You have some agents?
Strategies.
Yeah, the strategies, the action available to this, and
Function from values.
correct, like how each of our actions impact the other. Those are basically, it seems like, the basic ingredients. Okay. So, now we saw that with two players we can represent it sort of in this kind of way, in a matrix form game. They are also called bimatrix games and so on. You can also have like two matrices drawn side by side, where basically you just split whatever I wrote as a comma, you basically represent with two things. Now, formally, but we do not just want to talk about two player games, because like the traffic routing problem, we know we do not really necessarily know how many people are actually on a road at a given time. It is some finite number, but we do not know, right. So, we want to abstract, we want to make this as the definition as abstract as possible. So, then there are different ways of defining. We will start off by this one very standard way of defining called normal form games, and we will stick with this for some time, and then okay, it's called NFJ. They basically generalize this setting where the first ingredient is number of players denoted by capital. So, usually this is how I use, this means the set 1 to n. Okay. This allows me to index the players as 1 to n, it does not matter. So, AI is the actions available to player I. Okay. For each I, you have AI, correct. Now, because as we discussed that really one person's action does not really matter, because what really matters is how they are interacting with each other. So, we define this object, it is the direct product space of each of these sets, of all these sets taken together. Okay. So, this sometimes is called the action space, of the game or so on and so forth. Okay. So, this basically just consists of an element of this is a vector. It is usually written like this. So, here A1 small a1 is an action from capital A1, A2 is an action available to player A2 and so on. Now, in this game the action space for both the players were exactly the same. That is not necessarily always the case. Okay. You can have AIs to be vastly different. Okay. So, this is why we write it in this way. AIs do not need necessarily be the same thing and so on. This just means choose appropriately, each position coordinate is associated with a player uniquely. Now, so this is what is called the action profile. Action profile is the term, standard term used in textbooks and other resources. You can call it action vector and think of it as just an action vector. So, each AI is action of I in this vector A hat. Okay. All right. Now, we define the, so normal form game is defined by a tuple okay. It is a triple, number of players, the action space and the utility function. So, the utility function is basically again a vector of individual utility functions, okay, where UI, what do you think UI is a function? What would be the domain of UI? Yes. Why is it A? Yes, because again my utility takes into account all the actions of all the players. Okay. So, this is how a normal form game is defined using three triples: players, their action spaces and a utility function. Okay.
Are we assuming that all the players make the moves at the same time?
Sorry Malak, can you repeat? The voice is a bit muffled.
Are we assuming that all the players make the moves at the same time?
Okay, in this case none of that matters as far as the game description is concerned, like normal form game. In certain games, yes, I will mention precisely whether we are talking about simultaneous games or we are talking about sequential games and so on and so forth. There are multiple variations, but as far as this is concerned, there is no really would this definition really change based on whether it is sequential or simultaneous, multi-round or single round? So, this utility function is just saying for one particular, if we all act together or act in sequence, whatever, based on what anybody has acted, whatever the order, sequence and protocol we may have agreed upon, the utility function, utility value of agent I will be computed using UI. Yes.
So, I was just thinking of an example where, let's say you have a single road and there are cars in both the ends and the road can have only one car at a time.
Yes.
So, both cars, if the first car decides to go and the second car later decides to go, then the first car would have traveled some distance and the second car doesn't do anything.
Okay. So, in that sort of a thing, so in this case, okay. So, but tell me in this situation, what is your idea of a payoff?
How much?
So, no, yes. So, how much is the waiting time? No, you have to tell me how are you quantifying the payoff. So, there are two cars travel the same road.
They travel in the same speed. If it's a simultaneous move game, they meet in the middle.
But is meeting in the middle the, like you have to say the payoff, like meeting in the middle, whether or not we meet in the middle, is that what will decide their payoff? Like what, as a car driver, what is it that I am trying to maximize or minimize?
The distance I go in the road.
Still the same between.
Okay, so here is a road. Okay, let's decide. So, am I just trying to see how much of this road I travel before I meet the other person?
Yeah.
Okay, in that case, this game has a single winner, whoever starts first. If it's a sequential game, right? If it's a simultaneous game, then the speed of travel will decide who gets to travel more. Correct? So, okay, all games don't necessarily give equal opportunity of winning to all agents. Some games can pretty much stack the odds in favor of who goes first or second. Is that clear? But be that as it may, that scenario also can be captured using this description, right? So, in that case, the action space would basically, this would have to encode in the fact that if people go in a certain round, in certain, they take certain order, in this example at least, I go first or I go second and so on, how that will decide. So, AIs, right, action available, going first, going second, all these things would be part of the action space of those players. So, me going first versus me going second is quantitatively different. So, that is a good question. Okay. So, this definition is on purpose as generic or abstract as possible, so that it can capture as many scenarios as possible. Okay. But still, does it capture all possible game situations that you can think of?
I have just one thing in mind. So if we are taking like simultaneous, we are playing for infinite rounds.
Okay.
In that case, like how do we define the action space? Right?
Okay. So, again, in infinite rounds, this would tell me that all this is saying is that I play this, I play that, you play this. This together gives me this utility, gives you this utility, and the third person this utility. Okay. This particular thing, so this is that vector. If you go on, so necessarily the way the simple case would be, this is a one step, one round thing, and each round, as long as we do the exact same thing, the payoff will be the same. Okay. So, that actually brings me to this. If we were to imagine a multi-round game in which the history matters, think about chess.
So like you were saying, we can abstract away some finite sequences from.
So, I am saying at this thing captures the sort of situations in which the entire utility depends on what actions each of us are taking at this moment, and at this moment might not necessarily mean we are all playing together, but after the game, after we have played whatever we had, maybe following a protocol, but this is the situation, it is the reality, and based on that the utility is dependent. Now, imagine a situation where the history matters, like how I got to this particular, when was this does, so if I play a multi-round game, let us consider chess. Okay. You have let us assume we have the same moves available to us if we have those particular pieces on the board. That never changes. If you have a certain piece, the moves available to you are always the same. But based on what you had at the very beginning of the round, very beginning of the game versus several steps down, obviously the payoff evolves over steps of the game. That is the sort of game that normal form games do not capture. Okay. More generally, if we were to play a multi-round game, where, okay, so in chess what is happening is I am losing certain pieces, and therefore I can't play the moves again. But even if that was not the case, think about a situation where I have the exact same pieces, but now if I play that piece, I somehow get a different utility, different value than I would have in an earlier round. Okay? In those situations, the history of play matters. and those games are captured under extended form games, or sometimes also you may have seen them as decision theory proofs and so on. Okay, it is the same kind of an argument. So, we will get to that at this thing. Okay. So, but this is the most basic sort of idea of a memoryless game. You can play a memoryless game over several sequences. What that just means is, if you play the same strategy at step 1 versus step, all of us play the same strategies and play step 5, the payoff will be exactly the same. Okay? All right. Okay. So, okay. Also let us assume here that it is a finite normal form game. Okay? Finite here means the number of players are finite, the number of actions available to the players are finite. Okay? So, when we say finite games, unless explicitly stated, this is what we mean, number of players are finite as well as the actions available to them are finite. Okay? So, the moment that happens, u is just a function that is defined over a finite set to real numbers.
Also, do we have any restriction on the nature of u?
Like restriction on?
Nature of u?
Not really. You can have anything depending on what game you are trying to capture and so on. At least the game description does not sort of prohibit you from any particular kind of view. Okay. So, now how are we doing? Okay. So, let us look at, by the way, does this game remind you of something? Have you all seen this? Yes. So, this is basically the sort of thing that is known as a prisoner's dilemma kind of a game. It is a very generic class of game, where these values really do not matter, and maybe a exercise could be to see that you can have, yes, okay, let us do this. So, Sanjay, I am just fabricating a question on the go. Will you copy this so that can you give a generic relationship between A, B, C and D, so that whatever this is, let us call it, this is action 1, action 2, action 1, action 2. Okay. A2, I can't pull this up, claim what would be the values of, I mean the relationship, okay, make it as general as possible. Okay, I will not work this out, there is just a bit, it is very easy, but it is fairly easy, I mean it is sort of like a puzzle like quality, I suppose. A relationship between A, B, C, D such that this action 2, okay, is, okay, I am using too many A2s, I guess, A's and so on. What should we use? Choice 1, no, C, what, x1, x2, ran out of variables on the fly, okay, such that x2 is the dominant strategy, okay, that way, okay. And so, this is one thing. Second question could be, I want, so this is one, I am sorry, it is horrible, I should, bad board management.
So, just a question regarding this puzzle. We are trying to maximize our space, right?
No, I just want you to, so we were saying that this is a common generic game. So, I want you to find a relationship between A, B, C, D such that this x2, so each of the columns and rows represent some strategy, right. So, that x2 is this dominant strategy, like everybody irrespective of what others are the other person is doing, x2 is the best course of action. That is what I mean by dominant strategy. Okay. The second question is, same question Now, you also want to make the constraint that x1 is the best strategy. The optimum strategy. Do you see? If they could actually agree on this, this really would be much better than whatever this is, right, -4, 0 and so on and so forth. So, the point is this, so try to show this so that this actually gives you the best possible outcome. Okay. Sum is meaning, or sum here minimum meaning because you are talking about delay. Yes, taken together, for both of them taken together, it is a best. So, that is why I wrote best. So, over here delay means like the smallest value, if you think about some payoff this thing. So, it is like best means that way. Okay. All right. Unique, okay, is not among the best, but the unique. Just playing around with numbers, it is not very complicated at all. So, not even numbers, like relationship. So, we are just trying to get some intuition for these things, like hopefully you will agree that some of the terminologies are common, make common sense, the definitions are reasonable, are actually quite naturally well defined, and then we can get to the more sort of abstract things where at least this part at least I think is fairly simple. Now, other examples of game. Okay. So, you said that utility function, you asked, somebody asked, right, the utility function, do we sort of require the utility function to be some any particular kind? No, this one does not require, but in cases where you do have special properties defined on the utility function, we may be able to use to logically think about the game. Okay. So, one such common scenario is this thing called, let us say, zero sum game. Okay. It is studied, it is particularly as the sort of this name suggests, what it means is so usually zero sum game is defined for two agents, but it does not necessarily have to be that way. Okay. All zero sum means is that the payoffs of the two agents for the same action profile should add up to 0, and there is a more little more generalization of this, it is called a constant sum game. Okay. So, for any this, let us define in terms of zero sum game, in terms of two agents only. What we mean is u1 plus A plus u2 is equal to some constant c. Okay. So, when the constant c is 0, you get the zero sum game. Okay. So, is this a zero sum game? No, right, clearly the way it is defined. Could this be made to be a zero sum game? Like, this is where this will come in, right. Like, is there a version of this game where the values are so adjusted that it does become a zero sum game? Okay. So, when you do this, think about that question also. Okay. All right. So, do you have an example of a zero sum game? So, a simple example would be, let us say it is called this game called matching pennies. Now, we used to play this game not exactly this way where, but it used to be this about taking turns, like who if you were playing it to break, if we disagreed on something, we would like flip a coin. If the coins were same, it would be like some weird version of this. So, if both, so first players payoff is if this is, so zero sum necessarily needs us to add up to 0, right. So, if I put this 1, then the other one gets decided -1. This is where this sort of becomes so helpful. When you have two players and it is a zero sum or a constant sum game, just knowing the payoff of one person basically determines the payoff of the other person, nothing more needs to be said. So, this game has a very succinct description, that is one other advantage. Here is this where basically you, the second player, the column player here wins if, okay, let me just write this. So, how would we interpret this game? If both two kids are flipping coins and if both the coins turn out to be head, then basically the row player wins. So, this is one and the column player loses. So, it is a win and loss thing, it is not like simultaneously we can both win. This on the other hand is if the two coins are different, then the second guy wins. So, no matter what happens, somebody always wins, but the question is how it is sort of aligned, who wins when. Okay, so clearly this is a zero sum game, right? Is there a dominant strategy here? Okay, good point. Here the strategy is basically, okay, we will come to the question, like what does strategy actually mean here? You are right, it is inherently a sort of randomized game, coin flipping and so on and so forth, but okay, basically here the action is still head and tails. It is just that I do not get to decide the action is decided by a flip of a coin, but still the action space is still well defined, head or tails, right. Whether the coin comes out head or tail, that is determined by a probabilistic sort of mechanism. Okay. Alright, so we will come back to this. So, in this case still can you still argue that does any one person have a possible course of how that course of action happens, I do not care, but is there something one person could do that will always guarantee this person a benefit? Is it clear why? You guys are not saying no, right? You are saying no?
No. There shouldn't,
There shouldn't be, right? Yes. Why?
Because if the second player chooses H, then best strategy is choosing H. But if the second player chooses T, then the best strategy is choosing T.
Right. It's so basically there is really no one way to argue that will take care of all possibilities. So this sort of a thing, there is a name for this. Okay. Okay, we will come to this. So, this is okay. So, zero sum game, let us call it zero sum game for the moment. Now, there is another category of games, let us call this the, right. So, equal value game, it is called common payoff game, yes. Okay. So, can you tell me by the name, by the term, what it actually should mean, and how should the utility function behave? Sorry?
Constant, some kind of constant. Instead of 0, it adds to constant.
U1 equal to U2 equal.
That's a constant sum game. This we are saying common payoff game.
U1
Like
equals
payoffs are
U2
equal
equals
for all cases.
It's equal. Equal for whom? Like so, ui of some action profile.
Yeah, it's equal to U2 of.
Yes, correct. This is basically it. As long as we take this action, all of us get the same payoff. This kind of thing is also called a team game. Okay, so we all together, whatever happens, we win or lose together. A very simple. Can you come up with an example of this other than like cricket? Yeah, any kind of team sport, I suppose, is a good this for this. But a very simple game is a type of a game kind of scenario that Sanjay was discussing, and so I was trying to understand why what it means. So there are two cars in the opposite side of the road. Okay, so the point is, if they both sort of take the opposite directions, like one is coming through left from this side, the other one is heading to from the right side, they will collide. So the only way they will both get so if they collide, they both collide. If one person passes through, the other person also passes through. So collision is the common payoff, or avoiding collision is the common payoff. Correct? So in that case, so this is left, left, right, right. So in this case, if the person from the other side is heading in the left, I am also heading in the left, we both survive. The other person coming from the right, I also come, we both survive. And here when there is,
You mean left of that person?
of course, how else do we measure left?
No, it's a frame of reference.
No, that is what I mean, like whoever is driving their left. Okay, fine. And okay, so to unambiguously understand this, avoiding collision whichever direction you want to, that is what I am saying. Okay. So, here it would be a very terrible minus infinity type of a situation, but let us say less dramatically it is 0 0, right. So, this is what would be called a common payoff game, also known as a team game. Okay. Also called coordination game, exactly. So, that was the sort of term I was looking for and I forgot. Okay. You have to coordinate some places it might also be called correlated game and so on. Okay.
In this example, we can make use of the fact that everyone is rational.
Yes, everyone is rational. Okay. So, but the point is, yes, everyone is rational, and so you can say that if I am seeing you move it, but this is a simultaneous game. That is the good point. Good. This is, see, this is where it makes a subtle difference. The game becomes meaningless if it is not a simultaneous game, because I do not want to die. Whichever way you are coming, I should really move in the opposite direction if it is a sequential game. If it is a simultaneous game, that is when it makes it something like a game. Okay. Or like there is an element of surprise whether I will die or not die. So, I am most certainly going to escape death. Yeah, it seems like a lot of, like most Indian traffic situations mimic this thing. I do not know whether I will die or not die, right. Yeah. Okay. So, what else was there? There are lots of other kinds of examples, but right. So, now, okay, good. So, we have seen all these games, right. So, so is it the case that I am always, so this is a cooperation game. These were inherently, the zero sum game is an inherently competitive scenario, right. So, are all games like this where you have competition, you have conflict or cooperation, or can we have like a hybrid situation also? Think about a game where somehow or can you imagine it, are all games one or the other?
Krishna's theorem doesn't fit in either of the.
Which game? This one? It does not fit into either one. Why? So it's neither a competition nor a cooperation game. But it is a competition. I mean, I want to go as fast as possible, and if cooperation was the way for me to benefit, then this should have been a thing, right? I'm kind of arriving at this defective strategy without cooperating, I mean, even after discussion, we agreed that I have a reason not to like do the correct thing. But that's not that I should not like, that's not the definition of cooperative games or so on. They are not like, oh, do the right, the thing that we are talking about, doing the right thing and all, these are just terms that I am fabricating as we are talking. Okay, a game as such does not have this idea of this is a good thing to do or bad thing to do. That's just very perspective driven. There might be a good strategy for everybody to take so that everybody can benefit. Okay, that can happen, and a person can individually decide this is the best course of action for me. But just to be precise about the terminology, this defective strategy that I was taking, which is not back off, that I arrived at irrespective of what you were doing, right. So, it is not a cooperation. It is not a situation where my entire utility really depends on agreeing with the other person. right?
Could you please come again?
So, here we agree that at least cooperate, it's not like a standard cooperation type of a situation like there, right. Like I arrived at this strategy of not backing off purely by arguing in an individualistic manner. A cooperation would basically require me to think about what the other person is doing, otherwise I get nothing. That is what the traffic light scenario describes. It's sort of a dramatic way of saying that if we do not cooperate, we both die. Therefore, both people have reasons to cooperate with each other. Okay? Think about this, like why it's not and why is it also not of pure conflict? Is it of pure conflict game? Is it? Okay. So, now let us think about this particular game. Okay. So, this game is somewhere called Battle of the Sexes. So, think about a boy and a girl. So, you know this in I do not know, do you all play baseball or softball growing up? Baseball and softball are basically the same game, it is just played by a different kind of a ball. Tend to be in US, at least in US and Canada, girls tend to play the softball version, they are just playing with a slightly softer ball, and at least the league is set up like that, and even I think the collegiate competitions and so on. But of course, the girls can always play the regular kind, and the boys are all obviously free to play the softball version also. Either way, it does not really matter, but people have told me that somehow people who are used to playing the normal version, they find the hitting is easier, it moves far longer distance and so on. Okay. So, basically this so the boys basically, so the boy would be very happy if they both play the same game, right, they are playing together, because ultimately that is the objective here is to play sort of together. So, let us say 4, but so the okay, let me just write this down and then we will see. Okay. Okay. Yeah. Okay. So, what kind of game is this? Does it fall into the this of any of the other games that we have seen? Louder.
It is cooperative.
Why? Wait, it's cooperative because? For each one, okay. But why is it cooperative? Cooperative necessarily means I kind of have to, we both agree what we should be doing. So, sometimes that means in this case, I suppose what that's, if they do not play the same thing, they both lose out. So, essentially this game is originally it was defined as a date night. People are trying to decide what to do. One person wants to go to the movies and one person wants to watch a game. Ultimately, they want to do the exact same thing. The question is what, right? They have preference over who likes to watch a game over a movie and so on. So, if they do not do the same activity, there is no value. These people want to play together, but somehow they agree that if both of them played the baseball, it would be that the boy's utility would be 4 and the girl is not 0, but it is lower than 4. Similarly here, but it is sort of let us say maybe it is harder for her, or she has not played baseball the regular version, so her utility is lower. Think of it that way. Here the situation is, it would be ideal if both of them, ideal for the girl if both of them played softball. Now, the guy would like to play baseball because that is what he is used to, but he does not mind, like it is better than doing something else. Okay? So, they will necessarily have to do the same thing to get any non-zero payoff. That is where the cooperation comes in, or coordination. Okay. So, in this case, could there be a dominant strategy in this situation? Could there be a dominant strategy? See, remember, dominant strategy means no matter what the other person is doing, this is the best course of action for me.
So if we draw a flow chart like that,
Okay.
but do we call the end point basically the dominant strategy then?
So depending on how you do the transition, like what is the transition?
So you might be able to jump from VV.
Okay, yes, let's do this. So let's see. So if suppose I start from here, does any of them have a reason of moving from here to here? No, right? Both of them is there. Do they have a reason from jumping from here to here? Yes, but then again, this and this are the only thing. Both of them have to jump. Unilaterally, there is no course of action anyone can take that will give them a best payoff. That's the idea. Okay, so this is what we will call a coordination or cooperation game. Now, this oftentimes is represented as a symmetric value. This would be 4-2 as well. Okay, sorry, this should be 3-4. Sorry. Yes. Okay. Yeah. So it's given, but I made it a little different. I made the value different. Does the logic change as such? So each of them, we agree, want to be in one of these things, right? Otherwise, their payoff is 0. But however, we see which is actually a best value outcome. This one together, because obviously the girl wants like this most, but for the guy it's still 3 and not 2, which would be this one. Okay, so be on the lookout when you're analyzing games like this. Sometimes this sort of thing, just a slight change in value can basically it's like the possible best optimum outcome can shrink drastically just by a small change of values. Okay, all right. So now there is this idea. Now we have talked about this dominant strategy. Now when we don't have dominant strategy, so people online, is everything okay so far? Okay, thank you. Okay, so we agreed. Let me write some no dominant strategy. Again, can there be a dominant strategy here? No dominant strategy. Okay. What about this? No, right? Okay. However, so if I had this situation where somehow I'm analyzing the game space in this way, I start by saying, okay, suppose I was somewhere here. Is there anything I can unilaterally do? See, in dominant strategy, we were saying no matter what the other person does, this is the best thing that I can do, right? That's what I was saying. Now, I restrict my argument a little bit and say that suppose my opponent doesn't change what they are doing, right? They don't change their action, but I am allowed to change. So, I am changing unilaterally. Okay? Let's call that a deviation strategy. I was doing this and then I am deviating. So, that would mean just moving one step like this or like this, because one other person remains the same, right. So, when I move like this, it is basically the column player is changing, right, because the row player keeps on playing the same thing. When I move down, it basically means that the column player is holding steady and the row player is deviating. So, this sort of thing is called a unilateral deviation. Okay. So, when such deviations are also not possible, then we call it a Nash equilibrium. Okay. So, when a dominant, let me write this a bit, a dominant strategy equilibrium is a, let us talk about pure, we are just talking in terms of action space. Okay. So, in terms of action, such that So, A okay, each AI is a dominant strategy. Is it clear? Each AI. So, I should say AI is dominant strategy for all. When such a thing happens, that is what when we call it dominant strategy equilibrium. Okay? So, an equilibrium is a profile, not one strategy. A Nash equilibrium is an action, let us call it a pure strategy Nash equilibrium. Let us just add this word, we will tell what is impure, I will just get to it. Okay? Is a actions profile such that, can you help me complete this mathematical statement, what it should be, how should I describe it? I just said it in words, if you can't, well, you don't recall, I will tell you, but just think of it. All I want to say is, nobody has a unilateral deviation. Say louder.
You will know some particular A is greater than all other available A.
What does it mean, all other available A?
The all other available actions for the particular.
So it's like for every
While all the other players are remaining the same, right? That's the thing, yeah. So, okay, so let me write it in terms of a contrapositive type of a statement. Okay, so pure Nash equilibrium is an action profile such that no player has, you guys can see this, right? Unilateral deviation strategy. Okay. So, what is a unilateral deviation strategy? So, a player I has unilateral UDS if there exists, has a unilateral deviation strategy from A bar, okay, if there exists some AI prime in its own action space such that the utility value by him changing to this new strategy while all others remain the same. So, this notation initially may seem baffling, but it is nothing complicated. It is just saying take the same action profile as A bar, just drop I from it. Okay? This is just a vector as the same thing, just from the ith coordinate I have dropped AI, and instead AI is playing, ith agent is playing this new strategy. This is strictly better than the utility this agent I was getting when all of them were playing this action. Okay? So, unilateral means literally I am acting alone, everybody is remaining the same. So, this is nothing but the same thing as written. If I were to write it in expanded form, it would be AI comma A minus I. Okay? So, pure Nash equilibria would be one where no player has such a deviation. Okay? Now, in this example, let us trace back our path. Okay, let us start from here. Does this have a pure Nash equilibria? That game, the battle of the sexes? Both are?
Both. 4, 2 and 3.
Okay, this you are saying this is the Nash equilibrium.
Both.
This is also Nash equilibrium, this is also Nash equilibrium. Why?
Because for 4, 2, if agent If girl will deviate,
Yes.
so
She gets 0. And the boy deviates, he also gets 0. Good. So neither this has a neither can this be a Nash equilibria, not this could be a Nash. This is a Nash equilibria as well as this is a Nash equilibria. What about these? They are not Nash equilibria. Why? Yes, both have incentive to change, and they'll both improve their payoffs. Actually, that's the reason why they cooperate. Right? Any one of them changes, and they will basically end up in a situation where they see that they have a better. They have better payoff with cooperation. Okay, so this is a. Let me. So the point of this is to show that while there is no Nash dominant strategy equilibria, right? So for dominant strategy equilibria, you at least have to have dominant strategy for each of the players individually, right? So we don't even have that, let alone equilibria. But this is also a Nash equilibria. This is also a Nash equilibria. They are of different values, but they are both Nash equilibria. What about this? Which again, this and this is a Nash equilibria, right? Good. Okay. All right. So what about this?
Nothing.
Why?
Everyone has a strategy to like when whatever way say a negative evaluation has a strategy to.
So if this person is here, right? If this is from here, this person just by deviating will improve his payoff. But similarly, from here, this person also has a reason to pay this thing, right? So each individual from any of these situations has a reason to deviate, and that's true about all the 4 things, right? So no pure strategy, pure Nash. We'll call it PNA. Okay. What about? Okay. What about this game? No Nash equilibrium. Why? From here again, no pure Nash equilibrium. Okay, why is this? Why is this not a pure Nash equilibria? Correct, and this guy also can improve by going to 0. What about this? Why is this not a pure Nash equilibrium? Correct, this guy can also go to this thing. Okay, all right. Now think again with this question again. Argue one way or another whether when we have an abstract, can there be some values A, B, C and D for which there could be a pure strategy Nash equilibria, and if not, then give an argument for this.
Why is -3 not a Nash?
Good question, good question. Yes, why is -3 not a this thing? Because this guy can move, no? The row player can move from no, but -3 to 0 it's improving, no?
Improving for the different person, right? The second number is the column players.
Wait, this is correct. Okay, okay, yeah. Okay, wait. So this is the column player strategy for column players payoff for being defective. So the if I just move along this, column player is not changing. The row player is improving, right? And he goes exactly. So this is a pure strategy Nash equilibrium. Yeah. This is also a dominant strategy Nash equilibria. But because dominant strategy is anybody like both of them playing defective is the dominant strategy equilibria, right? Dominant strategy is me playing the defective thing. Equilibria is a profile. So both of us playing the defective strategy is the dominant strategy equilibria. This also happens to be a Nash equilibria, pure Nash equilibria. Is it clear? Because of this logic, really, that if I move this sort of an improvement gives nobody, like going from here to here or here to here are two like symmetric things. From here to here, who is going to get an improvement? The row player, right? And there is no improvement here, so they stay here. Similarly, from here to here, the movement is basically for the column player, and it only goes down from -3 to -4. Okay. Now over there for all these values A, B, C and D, like whatever relationship you come up with here, a very generic relationship, okay, try and see does this condition always hold, okay, that will you always have a pure strategy Nash equilibrium. Okay, so just play with this abstract, this thing, and see what all things you can prove. Okay, so this is a game where you have a dominant strategy as well as a pure strategy Nash equilibrium. Okay, how are we doing time wise? Oh, okay, we have gone well past time. Okay, so then this is not a bad place to stop at all. So we will continue. Now I have a question from to ask each one of you. Next class is on Independence Day. So yeah, I know institute holidays and so on, but this is IMSC. We often teach during institute holiday. It's not a very big deal. Maybe it's I don't know. It's a thing. But the only issue is that this media, in order for us to do this broadcast, we need help of people who may not like. They are they should get a break and so on. So now you all tell me, would you all like to have a class? Then I will teach via Zoom. Else, if you don't want a class, then I will not teach.
Logistically, it might be a bit infeasible for us because the shuttle service.
You don't have to come in here. I'll teach via Zoom because this room will also not be open. So there is no point coming here. I mean, if I have to teach, I have to teach this thing via Zoom because so that they can also attend. Okay. So that's the thing. You don't have to come here. You can just attend from where. So my question is, can you all tell me, would you all not want to have a class, or do you want to have a class? Does anybody want to take pictures or something, or can I erase it? Usually this is the end of the day, so can I erase? Okay, so do you guys have any questions? I should also ask this. So tell me, oh, there was a few other, while you all decide, you can, so what do you think? Should I teach or not, Sanjay? Sanjay is always in favor of learning. He will never say no. But what do you think? Like, so before that, let me just say, so Sanjay will take tutorials and he will discuss all these questions, okay? So the time would be something that you guys decide with him, and given all the time constraints that all of you all are facing and so on, that can happen entirely remotely. So please try to solve. We'll post homework. Sort of it's a problem set 0, let's call it. You don't have to submit it. It's mostly a revision on basic probabilistic arguments. So because next time when I see you all, whatever, we'll talk about this sort of a randomized sort of extension of this idea of strategy, where basically people use don't just choose one action, but mix of actions, and that's how they basically get an expected payoff. Okay, so for that I need some all of you to be able to have some basic knowledge of probability theory. It's not very complicated at all, basic expectation, and down the road we'll think about conditional probability and all. So I want to give some problems for you all to solve based on that, and then so we'll post that today, later today, or by tomorrow. Okay. Okay, grade, we do it here, we give a letter grade here, but you guys in CMI have numerical grade. Yes, there will be homework, and there will be, so okay, so it's not actually up on the website. I'll put it on the website. I think it will be 30-30 the mid-sem and final, and the rest would be homework, and there will be a class presentation, like a paper or some result presentation. So as the time goes by, as we do more and more things, I'm going to put some sort of potential presentation material, so you guys can choose and see what you like and so on. Okay, so this is sort of part of being able. Yes, so that's the one thing. Can't we stick to this?
No, not this.
Not this, the morning time.
Several of us in CNI have classes like that.
So you guys would prefer this late time?
Yes, ideally.
When is Ramya teaching? Huh? She's not teaching Tuesday. Today you had a class in the morning, no?
Today it was
A special.
rescheduled because yesterday we heard that anti-ragging meeting.
Right. Correct. That scrambled many of our plans. Oh, he didn't even show up. They are keeping attendance. You know this, right? It's supposed to be mandatory. It's not whether you choose to listen to these messages. You have to. Okay. So, I just want to ask, would all of you prefer this time on Tuesday? People online.
Yes, ma'am.
Mola, you are from CMI, is it?
Yeah.
So, are you an undergraduate student?
Yeah, I mean BSc third. Yeah.
So, can you, just may I ask, are you all planning to attend regularly? The credit versus audit makes no material difference. I just don't want to create where you state your preference very strongly and I agree, and then it causes problem for others, and then like I just want there to be a general agreement that you intend to attend, that is all. So, yeah, I know about you, but then the point is, can you at least CMI people, can you all masters, undergraduate come to an agreement with respect to time? Now, the other issue is the location. We have to have this place free or a place where some kind of broadcasting is possible. So, that
Possible for you to come to see.
this again it scrambles my. So, when I asked you all for all these things last, it's now the semester has started and people have decided on timetable. So, this is the thing. So, when is it that you people want the class to happen? Me there or you here? What is it? Yeah, once a week I can travel. What day would that be? So, again you all have to come to an agreement for time. But okay, but just a show of hand, just tell me. So, you all crediting this course? How many? Okay, so here how many of you are planning to credit this course? People online. Molai, okay, and I don't even know, quite a few people are. So, I guess people who are there in their PhD, like super senior PhD students like Shushabhan, Sanjay, they are free all day to attend any class at any time of the day. Okay, so, okay. So, okay, it seems so only CMI students are the ones who are credited. Please, can you all come up with a thing that works for all of you?
There are a lot of conflicts.
I know. So, there's a reason scheduling is a hard question, even with reasonable, even within like small
The numbers seems to be
inputs.
variable. So I came to know about the undergraduate students yesterday.
And they were all writing the same email basically in sequential order of asking about timing and so on. So, this is the other thing.
Came up to me just yesterday. I did not know about the undergraduate.
Yes. So, your constraints are at the top of everybody's constraint because of your great interest from the very beginning and so on. So, I will respect.
I practically have no constraints. I will take one course at CMI.
Based. Okay, then you keep your constraint loose. Okay, so other people, especially the undergraduate, they have to have a certain. So especially the second year undergraduate, are you allowed to take electives? How many electives? This is an elective, right? Oh, no third year undergraduates.
Third year undergraduates only have electives as far as I know.
So John and Soham, you guys are undergraduate students, right? So, okay.
Yes.
Okay, so from my CMI days, I can tell that our schedule was pretty, like there were mandatory courses and 1 or 2 electives. So, you just had to find something that would fit. So, I am just going to, so this time does not work for how many people? You.
I have a class right now.
So, you are missing your class to attend this?
I'll be late by 5 minutes.
Okay, fine. This is over. I mean, we can decide all these things. I'm just trying to get to a reasonable agreement because we are together. So you may leave. Don't like be late for this part. So your constraints, can you please write to me in an email? Both of you, John and Soham and others who are actually crediting the course. Okay.
Yes, ma'am.
Okay. Yeah. So whatever CMI, so I have talked to KV. I think they need like a grade of 4 and so on. We can do those. That's the least of a problem.
One thing I forgot
Yeah.
to